Okay, welcome back, everybody. We got with us Professor Xiaotao Sun of the School of Mathematics, Tianjin University, and he's going to give a proof of the finite dimensional proof of the Verlinde formula.
Thank you.
Let's welcome our speaker.
Thank you. Thank you. So, okay. Let me start the motivation. It is well known that the Jacobi, well done, the theta functions. It's recalled that if C is the smallest projective curve of genus G, the so-called Jacobian, we can consider it as a vector bundles of rank 1 and degree 0. It's modular space of the slam bundles. So we can fix a lam bundle type 0, then we have the well-known so-called Riemann theta divisor. Riemann theta divisor. This is Riemann theta divisor. Then, so we can say that this okay, should this divisor determines a lam bundle, a lam bundle. Oh, I forget this might be K is the power of K. I should write. Sorry. So it's the power of K. So it's classical theory says that the dimension of this space, the so-called theta function of all the K, is a power of kg. Okay, it is the proof is quite simple. I mean, you need to do some because this section can be realized as some kind of like theoretical functions. Then you can use a Fourier expansion and do some linear algebra. Now you can get this formula. This is rank 1 case. So people usually call such a theta function called abelian theta function. Okay, what is a non-abelian case? So so you can observe that the Jacobi as a topological space, it is isomorphic to this representation of fundamental group of rank 1. So it's natural, and so what is this, the representation space of rank R, a unitary representation. So then after many people's work, so people realize that on this side, there's a natural structure of projective right, which in a sense, which is a modular space of semi-stable vector bundles of rank R and degree 0. So let's say semi-stability is introduced by Mumford. It's the story I was told by Lana Simha. He said he with psychology first found that they construct a manifold which is indecomposable vector bundles. Now he, after knowing that stability introduced by Mumford, he immediately realized this might be the same. So he did this correspondence. Okay, his so-called non-Simhan suggested correspondence. So anyway, this is a non-abelian case because UR is when R is larger than 1, it's non-abelian. So we can consider the section, the global section is a non-abelian theta function or called generalized theta function. So it's a natural question for mathematicians. What is the dimension, the formula? So until, I mean, now we know which with the help of physics, we know this formula now. For example, when r equal 2, we have such a formula. So it's clear without the help of physics. I mean, mathematicians, in fact, it's rather difficult to make conjecture of such a formula. That is the reason after mathematicians know such a formula, so they try to understand the mathematics behind this formula. So not just, to prove such a formula. So in the last century, there are many people work out many proofs for different cases. Okay, so it's a lot of proof. So to prove this formula, in fact, one need to prove a more general case. Okay, let's record. We can consider more generally moduli space. So let's say it's a projection curve with at most one node. Okay, then this is a depth. Let's say find the side of smooth points. These are given positive integers. These are non-negative. It's non-negative integers. Set for such a condition. So there is a projective right which called the moduli space of semi-stable parabolic shifts of rank R and degree D on C with parabolic structure determined by this state. This looks complicated, but in fact, with this state, we just gave a representation, a reducible representation of GLR on that point. We will see this. So, what does it mean? So first of all, a torsion free shift has a parabolic structure of type. Those number, those are given the type. A given type means the filtration of this. These are vector space. So the flag of quotients and their dimension, the difference of a dimension are given. Those are good. Which are fixed. So we must fix this. Fix the type and the sequence of this integer. This you consider this is a point of a flag manifold. Okay, now this flag manifold, the Picard group. The Picard group has so many generators. So those sequences you can consider as a given number. On this flag manifold. So it is well known like the GLR, for example. The flag manifold is in fact a GLR moduli parabolic group. So those numbers determine the lambda on this group. It's in fact an ample lambda on this group. On this flag manifold. Then you take the group sections, the space. It is a irreducible representation of GLR. Yeah, X is a point. So I fix a point. Then the chief take the fiber. It's a vector space. Then the vector space you consider the flag manifold of this vector space. So on the flag manifold, which is given an ample lambda by this number. L of x, it's depend on the type of this. Because this depends on this number. It's a given type. For example, if you take L of this are 1 equal to 1, the so-called full flags. Then this Lx is just the R plus 1. R is the rank of. Yes, its Lx of course depend on the type. So the type is fixed. So at each point I fix a type. I fix this number. Yeah. Of course, for different x, I have different type of lines. Yeah. So what I said is means that those are in fact just a given representation of irreducible representation of GLR. You can consider I have a curve, have a vector bundle on. There are finite number of points on the curve. On each point, I fix, in fact, the vector bundle plus a representation. Yeah. So it's called a parabolic shift. So similarly, you can define. These are fixed notation. You can define the degree, so-called parabolic degree, because we try to work on the single curve, so it's convenient to use this Euler number. Binomial is equivalent to some kind of degree. So you can define this. You can also similarly define this semi-stability. Now one can construct the moduli space. So there is a semi-normal projective right, which is the cosmoduli space of the semi-stable parabolic sheaf with fixed of rank R and degree D, with parabolic structure of type and width fixed. So if C is small, then this is normal projective with only rational singularity. Okay, so I have such a formula. I have such a projective right. So then we can similarly define the so-called theta line bundle. I don't want to go to the details. So anyway, you use this number. You can define such a ample theta line bundle. So it's a theta line bundle. So that the space, we call this space generalized theta functions or non-abelian theta functions. That's many and there are other order also called non-abelian theta functions. So the dimension, the vector space has a dimension. So what is the formula? This formula was predicted by conformal field theory. I will go to the. I don't want to go to the proof, the detailed proof, but I try to explain how it comes from the physics. Because there are many works. So in fact, we give. The formula looks like this. There are many kind of versions, in fact, of the formula. So we first to find a version of this formula, which I try to convert it for our proof. So the formula looks very complicated, but it's computable anyway. So those are clear. This number appeared. I only the summation is to take one of this set of integers.
No, after the first line, but it's a sum.
Let's say sum.
No, before the sum, it's like the whole thing, right?
Yeah, the whole thing. This is a number times the sum. Because it's too long. So it's continuous. Okay. Yeah, it's very complicated looks. So that's is why I don't believe how to conjecture such a formula.
Special case of a formula which looks much simpler.
Yeah, but this is what I try to find. I find I would like to get the formula of this number without know the right side. Yeah, I will say after I explain, you will say that at first the simplest case we know is some number which is 1 or 0. I mean, the simplest case you will get the modular space, you get 1 point, so its dimension is 1. Now it has become complicated. You can understand this number is get from 0, 1. So very complicated the combinatorial way to plus together. Yes, yeah. Okay. Anyway, so yeah. So all of this are computer. I don't want to. I think I don't need to because nobody can remember this. But you know that I don't think that still without the help of my physicists. I mean, I don't believe this. Anyone can conjecture get such a formula. Okay. Okay, why? How it's related to the physics? So I don't know. I'm not an expert of physics, but from one can formulate in a mathematics way. I mean, so the so-called theory is so fix a finite set, which is evolution. Okay, that's the so-called theory is I should not say this is a function. It's an association. So you get you give a curve is stable curve, and a finite number of points, small points, and such each point corresponds the element of lambda 1 lambda is in this. So you should associate a vector space. Okay, this vector space could conform blocks, something like this. I mean, those associations should satisfy this exponents. For example, P1. This means that those puncture points are empty. Without puncture points, that is should one-dimensional, so one-dimensional space, and also equal. It's invariant under the evolution, and we should have such a decomposition. And the important is if this family degenerate, I mean you can move this in the family, then the canonical isomorphism. There should so it means that those vector space should be independent of the complex structure of the curve. I mean, and in particular, when this degenerates to some point, for example, has a one node, then you take the normalization, then you should get this decomposition. Yeah, this is a requirement. So with this, you can formally do the computation. So from the definition, this only depends on genus. So you can formally write this way in this one. So you can you can consider that a function. The x is here. So this is the dimension. So those requirement, those requirement can be formulated that means this function should satisfy these conditions. Oh, sorry. First of all, you can use this formula to reduce everything to genus equal to 0 case. So you can reform in this called Fashion rules. I mean, Now use this function rule, you can define a function ring. So let's say finite side, you can take the free abelian group. Then you can use this number to define the product. So anyway, let's say you get a ring. So once you give this, you get such a function ring. Then you can get the formula. I mean, if you know the errors of the character of this function ring, then you can compute this dimension, use this character. That's our general formulation. So of course, which is related to the algebra geometry. I mean, it's an example called the model. So you should give such an example, I mean, association, which satisfies this. So this is a famous paper that just proved the following. Said if you give a simple complex linear algebra and an integer k, now anyway, this is quite complex. Use the representations of this alpha linear algebra. You can associate. You can get the association. I mean, like you can get such association. This in fact become some kind of, I mean, representation of the algebra. So this paper, and the paper has been quite famous that prove that this association satisfies this requirement. Okay, in particular, in this example, the function ring is a free abelian group of the irreducible representation. PK is okay. PK is a set of dominant weights of this K. I mean, the free group means you take tensor product. I mean, there's some kind of free group. Then you define the product again. So it's a function ring. So now if you try to compute this dimension of this space, according to this, you have to determine all of the character of this function ring. In fact, the so-called Verlinde formula, I mean, according it's conjectured by Verlinde. It's not really proof. I mean, but it's conjecture. Okay. Okay. So why this example related to algebra geometry? It's because this is well known. It's called a double quotient. I mean, this double quotient is identical to the stack of principal G bundles. I mean, G is an algebra group determined which with the algebra of G of K. I mean, this example is given a simple algebra G. So there is an algebra group, so that it's corresponding to this algebra. Okay, so I say it's certain. Then some mathematician, I mean, many people, I mean, I don't want to mention it because it's impossible to mention all of the people. So the first one might be it's a simpler case. I mean, without the puncture points, only for this G. I mean, for this G, they find the space in fact is kind of global sections. This gives the relationship with algebra geometry. Okay, for this group, I mean, was generalized to the puncture case. I mean, is by Pauli. Okay, in fact, only recently I found this resource, but I didn't go to the paper. I only get this from the math review. I mean, they approved this resource. But I quite, you can say that this is a finite dimensional space, right? When C is a single curve, the parabolic bundle is not compact. In fact, for example, for vector bundle case, the stack should has is not compact because there are many objects with a lot of vector bundle. In fact, it's considered a divisor. So it is not clear, I mean, from algebra geometry. This open side, this non-compact and the group section. I mean, why this space is finite dimensional? It's, in fact, for me, it's not clear this side, but this identification tells you that this must be finite dimensional. I do not say why. I mean, so it means that the mathematician, the many mathematics which we do not really understand. I mean, of course, maybe I don't know why this holds. I mean. I would expect those children is some kind of compactification. I mean, but anyway, this is the resource. But it's deserved to be understood quite well why this holds, why this is a finite dimensional space. Anyway, so now in fact there are many proof. I mean. When you say Verlinde formula, there are many understanding. So it's the question, faced by for Faltings, he has a paper called a proof for the Verlinde formula. So he was asked a question by the reference. This I copied from his introduction in his paper. Okay, he said the reference has asked him, to remark that there are several interpretations of the term Verlinde formula. So he said one is the equality of the dimension for the space of global sections under the analog of the conformal field theory. And this is proved here. He said he proved this identification. Something like this. So it's called Faltings independent. He proved this equality. He said this is one interpretation of Verlinde formula.
That would imply what you have here, provided you can really prove that that what they are doing, everything happening from yours, and that part is probably not.
Okay. One is the quality he said here. Another version is an expressive formula for these numbers. So it follows from purpose and from certain factors about the integral representation of Cosmology. I guess here he said expressive formula for those numbers. In fact, he means that this side, the dimension of this formula. Because we know that how to compute this formula. If you know the, this is Faltings means. And then he said, according to experts, those facts are true. But he said, what is those facts? In fact, he proved those factors for some groups. for some classical groups. But he put the general case as a conjecture. This is conjecture. So, in fact, it's how to determine error of the character. I mean, means that if you know this fact, then you know this number. I mean, but at least at this time, Faltings said he put this as a conjecture. Well, of course, this conjecture is proved by recently in this book. I mean, okay, in this book, he tried to prove everything about the Verlinde formula. Was, I mean, something which is not proved, but many people use. I mean, as Faltings says, I call that true and no. Okay. Okay. This is many Faltings do this. In fact, as Beauville says, there are many proofs. I mean, basically, we can say there's two kinds of proof. One is, one is that you use this equality to relate the space of group sections to this space from physics, then to compute the dimension of this called conformal blocks. This is one way. It's called this is what he said. So he could infinite dimensional proof. And another proof is that we just forgot this identification, this equality. We prove this directly to prove the right hand. I mean, just in a sense in the algebra geometry. Of course, we get ideas from the physics, but we compute the dimension do not go through this isomorphism. I mean, just purely in the this is called Beauville says, so use standard algebra geometry. But when he read this wave paper, I mean, it's many years ago, he said only for some special case. For example, use Riemann-Roch theory, you can compute this number. But of course, you need to compute the intersection because Riemann-Roch theory, you still need to compute the intersection. Intersection theory. And this is another proof for all of this for rank 2 for spaces, and also this. And this is in a differential geometry method. Differential geometry method, but it's only for G at least 2. You will select when G equal to 0. In fact, it's quite complicated also. Okay. Of course, after Beauville's paper, there are some progress. I mean, for R larger than 2. For example, in this paper, it's called the intersection theory on this. Okay, this is a modular space of in this assumption, it is stable vector bundles of a fixed determinant without the parabolic points. So in this case, this is a small projective right. I mean, with Picard group. I mean, it's generally sacred group. So, then in their paper, they of course might work out the intersection theory. In particular, you use Riemann-Roch theory, you can implement the Verlinde formula for this case. And there's also, there use a different way to to work out the intersection. And in fact, Jeffrey tried to generalize this to the parabolic band case, but I still need to put this condition. I mean, I should emphasize that when you assume this condition, then the modular space of parabolic bundles, I mean, this modular space is a product of flag bundles over this modular space. Because if you require this very small, then parabolic semi-stable is stable, because this is only stable. So it's at this condition, so the parabolic bundle is stable if and only if the underlying bundle is stable. So this modular space has a good relationship with this modular space. This one is just some flag bundles of this modular space. So you can generalize when you know this intersection of this modular space, you can generalize to this one. So it's so this assumption is very important here. It's essential, in fact. So let's say another analytical proof if they are related this to the index of some operator. Still, this large enough is equivalent to this condition, in fact. I should okay. Maybe go back to say this actually. Something like this. When k large enough means this number will become very small. You can make this very small. So in this case, the probability, I mean, there's no difference between parabolic case or non-parabolic case. So it's quite so the okay. Okay. So I should say this and this are these two assumptions are the same. So it makes that the modular space of parabolic bundles is a flag bundle of this one. So it's make it much easier to compute. So of course, if you know the one-issue theory, or as their comments that this results compared with rational one-issue results gives a new proof of one-issue. This, huh? This. Oh, this is not a resource. This he wrote a method review in the method review of this paper. So just the comments. Yeah, but you know, in the method review. Yeah, no, he read a review. I mean, for this paper. In the method review, he said this results comparing this games. Yes. Yes. I know that he tried to rework out the proof. Yes, I know this. Yeah, in fact, I wrote a few emails to Telema about his proof in this paper. At first, he answered my email, and then second, I asked further that how to because I also worked on this one-issue theory. I asked how to overcome those difficult points which I made. Then there's no answer. And I also was told by many people that Bismuth tried to rewrite the proof, I mean, of this one-inch theory. But Bismuth said that he tried a lot, I mean, cannot work out. So anyway, so this one-inch theory for general case is still not, but for many groups, we have a different proof, in fact. We have a different proof. We use the modular PK method. Okay. So I will those are the, though I will explain what will work. I mean, we of course get the ideas from the physics. So we take the degeneration, a family of curves, smooth curve, to a single curve. The single curve with one node point. I mean, it could be irreducible or reducible. Okay. So we need to prove two cases. One is the dimension does not change in this degeneration. So in this case, in fact, we need some kind of one-inch theory of the cohomology. In particular, we need the one-inch theory of cohomology for single curve, because when t equal to 0, this space is not normal. I mean, it's not a normal right. It's only semi-normal. So it's difficult to work out a kind of one-inch theory. But in order to prove this as constant, we need to prove both for smooth curves and also for single curves. Anyway, so the second, if I take the normalization of this one, now in fact we can work out the decomposition theory. This of course suggested by physics, but this really is only purely by algebra geometry in this side. So this is non-normal. It's not normal, right? It's a projective, right? But which is not normal. Now we have to take normalization. The normalization is again a modular space. Now we have to study the relationships and determine the error of the singularities. So it's, but of course it's good chance. I mean, for get motivation, we have the motivation to work out some mathematical results which we do not know before. I mean, so anyway. We know we have such formula. This gives if we know this, now we in fact get a incurrence relation. I mean, this is you can consider as a formula about the genus G, and this is genus G minus 1 because this curve has G minus 1, has genus G minus 1. So, but at that time, I only, yeah, sorry.
The last smaller side should make it small.
This one?
The very last.
This one?
Smaller than K.
Yeah, smaller than K. Equal. I mean, in this case, I only need smaller. Yeah. What is equal makes very complex, but technically complex. But finally, we get the same results. But you know, if you allow this equal, I mean, in the construction of the modular space, I mean, like call this. Yeah, this is technically difficult, I should say. Okay. So there's one, I mean, you can, if you allow this are equal, then the object in the modular space, I mean, we construct the modular space use GIT quotient. So you will get the non-torsion free sheaves. It must appear some sheaf which is not locally free, which is not torsion free, has torsions. But now you have to do. I mean, usually I take the module space GIT quotient of the quotient space. Then the quotient space you have to fix what is the singularity. Then you take quotient. But finally, you can prove that those sheaves are is equivalent to parabolic sheaves which are torsion free. So finally, you get the module space. The point is torsion free, but when you work out this, you have to do some other case. But anyway, those are. I saw the physics. It's smaller. Okay, so it's yeah. So it's smaller. Okay. So okay. So I have let's decrease the genus. But when you decrease the genus, you will see that this increase the number of parabolic points. So this gives you a possibility to decrease the number of parabolic. For example, you take x1, x2, p1. You divide the number of parabolic points into two groups. You can. But in order to have two recurrence relation, we have to prove the one-ish theory. But unfortunately, at that time, I only prove this one-ish theory for large genus. Okay, so it's if you remember the analytical proof, also only for genus at least 2. So then with one of my students, we can remove this assumption. We prove this one issue for when it's a smooth curve. We prove this one issue quite well. I mean, if it's irreducible, I mean with singular curve, we still prove this. We can still prove this. So. Once we have such a one-ish theory, now we have the two recurrence relation. Use this decomposition theory. One is decrease the number of genus. I mean, another. But in this case, you will increase the number of parabolic points. I mean, means x1, x2. Okay. Then this one can be decrease the number of parabolic points. So use this two recurrence relation, we can prove this formula. If we know, I mean by the mathematical induction, if we know the case G equal to, let me say this, okay. So we can prove, for example, now we how to prove this. First of all, we assume if G equal to 0, this equality holds, then it holds for any G. Okay, let's just directly use this recurrence relation. Then let's make some computation. The computation is looks but not difficult. In fact, okay, to mainly use such fact as representation of finite groups. Okay, anyway. Now we reduce to prove this equality for G equal to 0. Namely, C is P1. For many, so now you can prove that if this equality holds, if the number of parabolic points are smaller than 3, I mean 2, 1, 2, 3. If this is no, then This is no. So namely, the one in the formula is proved if we can prove this special case. It's a real special case. It's a P1. In fact, for this equal to 1, equal to 2 is easy. It's not difficult. So the only difficult case is P1 with 3 puncture points. It's also trivial when R equal to 2. R equal to 2 is trivial because the modular space is very simple. Relatively, it's when R larger than 2, I spend a lot of, I mean, if I assume this is true, in this case, then you can, for general case, you can take this is a union with one side is with 2 points. Then you can use this recurrence relation. This is 1, but when you go to here, when you separate these 2 components, at one point you have an increased 1 because x1 here, another x2 here. So this becomes 3-point case. 3-point case. These are of course can be used mathematical induction. So I use this. Okay. I always direct use here. Okay. So then you still hold this. Yeah. So I don't do this. So now I will. So our main work is focused on the 3 puncture point case. So first of all, let me explain a little bit here. Okay. Sorry, I should explain. Okay. 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 As I said, we gave such a data. In fact, in order to convenient to survey, we can from this data we can get for each x. Those numbers is given by this way. It's a one-to-one correspondence, but those much easy to say it's really related to representation. Right. So when you give this, you take lambda I is k minus. Then those the n1 is such n2 n2. Conversely, you gave me such a sequence here, so I can compare it. The first two you can get this number. I mean, so at one point you just put one such a partition here. So what why I say this? So one work on this 3-point case. 3-point case means for number first of all, I consider special case. 3-point case one, those 2 points we put any partition. But at one point I put a special partition. What is a special partition here? Is this partition? I mean, it means that the flag manifold is special and the weights are special. If I take it for this special, if at one point you take this special partition, of course this number is nothing. It's just the one in the number. There's a formula here. You can compute this number directly. I mean, just put in this. You can compute this directly. For example, you get this those number. You can compute them. Those compute is directly, but the difficult part is to compute this number because we try to prove that. First of all, I try to prove this number is equal to this number. Okay, so it's for this number, because it's just the formula, so I just put it in, we can compute it directly. Okay, but for this number, its size is a kind of modular space. I mean, there's number, and here you take a globe section. So to compute this dimension, you have to determine the modular space. The modular space. This is our K lemma. In fact, this proof spans more than 10 pages. So case by case to determine the modulus. But this is easy, okay. This is also easy. I mean, 1 point case. 2 point is side. Let's consider 1 point. If this one, because at this point is given a representation by this partition. This is gives a representation by this partition. This equality means that these two representations are dual each other. So in this it's 1 point. Otherwise it's empty. You have to. There's no such semi-stable parabolic bundles on P1. So when for 3 points, we'll also can prove that it's considered 1 point if this partition belongs to this side. This side is okay. This side is appears in the representation theory in many cases. Okay, sorry. Where I think we define this called the side of partitions, the integral orbit from lambda by this both. It's something. Okay. Anyway, this is one. Otherwise, it's empty. So, so corollary is these are equal. When these are for 2 points. For 2 points case, we proved this equality. But for 3 points, we only to prove the special case. Among the 3 points, there's 1 point we put a special, for special partition we put this equality. This proved by direct computation. We say that. But how to prove this general case? Then, if I put this a general partition, now we use induction. So now I prove this. I try to prove this in general case, namely this is any partition. The idea to prove this is to do some kind of induction. So for any partition here, we define this number. Okay, this number, and also this number. So we say that if when this number is equal to 0, that means this arc. This means that in this case, the point is we put a trivial representation. In fact, trivial. So it's come back to the 2 point case. So nothing to prove. So one is equal is different trivial polynomial. So the proof reduced to the case of 2. So we can assume this is larger than 0. Then we try to prove this equality by induction of this difference. Okay, that's difference. I mean, let's really spend, if I spend or sometimes, I mean, I don't know how to suddenly to really use to figure out to use to induction to this way. How to do this? So further one, this is equal to 0. Then this must be our special case. So this is by this case is worked out by direct computation. Of course, at least more than 10 pages, in fact. let's spend a lot of time to work in this case. So we can assume that this holds for any if this are smaller than n. So if for this partition, now we take this one. Now we consider a case with 4-point case because now I can use this relation for this 4-point case. First, I put this 2 in the group, this 2 in another group. Now I use the recurrence relation. Let's increase 100 point. Let's increase 1. I mean, I put this in this here. I mean, that's how different. I mean, the order are not important, right?
You are out of time. But,
okay. Okay. Anyway, in this you can you get this. I mean, there's one you can take out, but another. This is for L. Now, in this side, if you take this one out, it's becoming here. But for this, you can use induction. You can compute for the partition in this side, which side this one. So you can use induction. So I get the formula. But I can compute this in another way. Namely, this side I can use. In another way, I put this 2 in that group, this 2 in another group. I again use the recurrence relation. Then this already know that, so I get this. Now you can easily that if you use this already know that. So it's another computer another way. Now these are formula. I mean, you compute this directly. That's called one. We get this. Now this one you get this. So these 2 are the same. So it means that these 2 are equal. So it's cool. So then have no time. Okay. So I just forget. Okay. I mean, because I don't try to the proof of one in the formula. I mean, just take a look.
Any questions?
Considerably different from what?
Oh.
Can you say it's finite?
Yeah.
Or concerning the weight system of SLR, you can bypass some arguments that otherwise can.
Okay. Let me say that first of all, the proof. I mean, you can say that the so-called finite proof is dimensional proof is that we do not go through this equality, which is related to the physical space. Prove directly in algebra-geometry. So some other proofs, you know, says always require some condition. I mean, so all proof.
I understand, but the main aspect is that you do not need to do that because it's results about these recursion relations and
Yeah. But we still not understand well because as you say that the simplest case is this, right? But it does not give you many hints. It's 1 or 0. So we expect that for the simplest case, we can get a express formula which is can be conjectured for mathematicians, or for example for P1. But okay, I don't think we really understand. I mean, without physics, I mean, if you do not know this formula, how to get this? Yeah. Let's.
But for that particular case,
Uh-huh.
yes,
Yeah.
he knew certain numerical values. And in some simple cases for low values of A and low values of A, he just observed it. And then he checked for other cases that are to be true. And then mathematicians realized that this is not just the state, some version of conformal field theory, but you can rephrase it in algebra.
Yeah. Yeah, in fact, yeah, for general G, unfortunately, we still not have a purely algebraic geometry for any G. So you can say reasonably there. Because we do not know what is called degeneration for G bundles. I mean, as Faltings said, even for SLR, we do not know the degeneration of vector fixed determinant, because one sheaf is Tauschen-free sheaf. How to define the determinant?
Thank you very much.